Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome to the Deep Dive. Today we're looking at something that feels like it's straight out of science fiction. We might be at the end of a hunt that's been going on for, nearly 100 years? The search for dark matter.
It's the biggest piece of the cosmic puzzle, and it's been missing this whole time. We're talking about the invisible structure, the scaffolding that holds literally everything together. And for decades, it's just been, a number in an equation, a gravitational ghost.
That's such a good way to put it. And our mission today is to really get into a new finding that is so specific, so tantalizing, that it has the entire physics community buzzing.
It really does.
We're going to be unpacking the work of Professor Tomonori Totani from the University of Tokyo, using data from NASA's Fermi Gamma-ray Space Telescope. And the claim is huge. They think they may have finally seen it.
Or at least seen its fingerprint, its direct signature. We're going to connect the dots today, from the, abstract theories of the 1930s all the way to this cutting-edge space telescope data from 2025.
And we're using the study itself as our guide, the one published in the Journal of Cosmology and Astroparticle Physics.
Exactly. Because this isn't just about finding something new. If this is right, it's the discovery of a brand new fundamental particle. Something that would force us to rewrite the standard model of particle physics.
Okay, so let's unpack that. If this really is the smoking gun, it means that 85% of all the matter in the universe is made of stuff that is fundamentally different from anything we have ever seen or cataloged.
Right. The implications are just staggering.
So we have to approach this with, a lot of critical thinking. We need to understand not just what they found, but why on earth it's taken us this long to get even a glimpse of it.
Precisely. To really appreciate what a massive claim this is, you have to understand the decades of, frankly, frustration and dead ends. And that journey starts way back at the beginning. Why did we even think this invisible stuff existed in the first place?
Okay, so let's set the scene. We're in the 1930s. Our understanding of the universe is still pretty new, but it's built on these pillars of classical mechanics, Newtonian gravity.
Right. And the assumption was simple. What you see is what you get. If you want to know the mass of a galaxy, you just add up all the light from the stars, estimate the mass of the gas and dust.
And that's your total mass. That tells you how much gravity it has.
Exactly. And this is where the Swiss astronomer Fritz Zwicky comes in. He was this brilliant, though apparently very cantankerous scientist.
I've heard that, yeah.
He was studying a huge collection of galaxies called the Coma Cluster, and he was trying to measure how fast the galaxies inside it were moving around.
So he's basically timing the speed of this giant cosmic dance.
A very, very fast dance, as it turned out. He did the math. Based on all the light coming from the cluster, all the visible matter, the galaxies should have been moving at a certain speed, but what he actually measured was just wrong.
They're moving too fast.
Way too fast. So fast, in fact, that the gravity from all the visible stars and gas wasn't nearly strong enough to keep them from flying away.
Wait, so based on the laws of physics, the entire Coma cluster should have just disintegrated.
It should have flown apart billions of years ago. The galaxies were moving with so much energy that the cluster's own gravity couldn't possibly hold them in orbit. It was a massive paradox.
So Zwicky had a choice. Either Newton's laws of gravity are completely wrong, or there's a whole lot of mass in that cluster that he just can't see.
And that's the conclusion he came to. He was confident in his measurements. He reasoned there had to be some other source of gravity, an enormous amount of unseen matter holding it all together. He called it Dunkelmaterie.
Dark matter. And people didn't exactly jump on board with this idea, did they?
Oh, not at all. He was largely ignored, even ridiculed. The idea that maybe 90% of the universe was made of some invisible, unknown substance was just too radical. People thought, it must be an error in his calculations or some dust we're not accounting for.
Just a weird anomaly.
Exactly. The idea was just shelved for decades. It was a theory way ahead of its time.
But the evidence didn't go away. In fact, it came back with a vengeance in the 1970s with astronomers like Vera Rubin and Kent Ford.
And that was the pivot. That was the moment this went from a weird idea to a fundamental problem in physics. Rubin and Ford weren't looking at giant clusters. They were looking at individual spiral galaxies, like our own Milky Way.
And they were measuring how fast the stars were rotating around the center of the galaxy.
Right. And you'd expect something similar to our solar system. Mercury moves really fast, Earth is a bit slower, and Neptune, way out at the edge, is just crawling along. The further you get from the central mass, the slower you go.
But that's not what they found in galaxies.
Not even close. They found that the stars way out on the fringes of the spiral arms were moving just as fast as the stars near the core. The rotation curves were flat.
Which is impossible, unless
there's a huge invisible halo of mass surrounding the entire visible galaxy, extending far beyond the stars. Its gravity is what's keeping those outer stars in their high-speed orbits, stopping them from flying off into space.
So after 40 years, Zwicky was vindicated. This wasn't just a quirk of the Coma cluster, it was everywhere. Every galaxy seemed to be embedded in this massive, invisible halo of dark matter.
It went from being a curiosity to a cosmic necessity. And that raises the billion-dollar question that physicists have been wrestling with ever since. If this stuff makes up 85% of all matter, why can't we see it? Why is it so incredibly elusive?
And the answer gets down to the fundamental forces of nature. It's all about what it doesn't do.
It's all about the electromagnetic force. That's the force that governs light, electricity, magnetism, basically everything that makes matter visible and interactive. Particles interact with photons, which are particles of light.
They can absorb light, reflect it, emit it.
But dark matter particles, whatever they are, they just don't seem to play that game. They have no electric charge. They just ignore light completely.
So a particle of dark matter could pass right through you, right through the Earth, without hitting a single thing. It's completely transparent.
Which makes it invisible to every telescope we've ever built. We only know it's there because we can feel its gravity. We're trying to study a ghost.
So if you can't study it with light, you have to find another way. You have to hope it interacts with one of the other fundamental forces, even if it's just a tiny, tiny bit.
And that's exactly the strategy that led scientists to the leading theory, to the WIMP hypothesis.
Okay, so if dark matter ignores the electromagnetic force, scientists had to place a bet. Which of the other forces might give us a clue? And they landed on the weak nuclear force.
That's right. And this led to the dominant candidate for what dark matter could be for a long, long time, the WIMP. It stands for Weakly Interacting Massive Particle.
And it wasn't just a random guess, right? This idea came out of other bigger theories in particle physics.
Exactly. It emerged naturally from theories like supersymmetry, which proposed that every known particle has a heavier superpartner. The lightest of these superpartners would be stable, massive, and would interact via the weak force. It was a perfect dark matter candidate just waiting to be discovered.
So let's break down the name, weakly interacting. Why is that part so important?
Well, the weak nuclear force is one of the 4 fundamental forces, but as its name suggests, it's incredibly feeble and only works over very short distances. It governs things like radioactive decay.
So if dark matter particles interact through that force, it would explain why they're so hard to detect.
It would.
Yeah.
It means they would stream through normal matter, through us, through planets, almost all the time without ever hitting anything. An interaction would be an incredibly rare event. It solves the elusiveness problem perfectly.
Okay, so that's the weakly interacting part. What about massive?
That's crucial for a couple reasons. First, they need to be massive enough to clump together under gravity and form those giant halos around galaxies that we see the effects of. Light particles wouldn't do that.
And the second reason?
The second reason is key for actually finding them. If they are massive, say hundreds of times heavier than a proton, it gives us something to look for. It gives us Einstein's famous equation, E equals mc squared.
Ah, okay. Mass can be converted into energy. And this brings us to the really clever part of the whole search, the annihilation signature.
Right. If trying to catch a single WIMP is nearly impossible, what if we could see what happens when 2 of them collide?
Okay.
The theory predicts that WIMPs are their own antiparticles. So when 2 WIMPs zipping around in the dense center of a galaxy happen to crash into each other,
They annihilate, they just vanish.
poof, they're gone. But their mass can't just disappear. It gets converted instantaneously into a shower of pure energy.
And that energy creates other particles that we can detect.
Exactly. It produces a whole cascade of familiar standard model particles. The heavier the original WIMP, the more energy is released, and the heavier the particles that are created. Things like quarks or even W and Z bosons.
Now, those are heavy, unstable particles. They don't stick around for long, do they?
Not at all. They decay almost instantly. And in that decay process, in that chain reaction, they produce the final stable thing we can actually look for from Earth.
Gamma rays. High-energy photons.
High-energy gamma rays, that's the smoking gun. The WIMPs disappear, they create these heavy, unstable particles, and those particles immediately fall apart and release a flash of gamma ray light.
And the beauty of this is that the energy of that gamma ray is directly connected to the mass of the original WIMP that started the whole thing.
That's the fingerprint. It's a direct line. If you can measure the precise energy of the gamma ray, you can calculate the mass of the dark matter particle that created it. It's no longer a ghost. It has a specific measurable property.
So the whole strategy for the last few decades has been find the place where dark matter is densest, point a gamma ray telescope at it, and look for a specific spike of energy that can't be explained by anything else.
That's the game plan in a nutshell. And there's one place in our neighborhood that is by far the most promising hunting ground.
The center of our own galaxy, the Milky Way.
All the models show that our galaxy is sitting inside this enormous sort of football-shaped halo of dark matter. And the density of that halo gets higher and higher the closer you get to the galactic core.
More density means more WIMPs packed into a smaller space.
Which means a much higher chance that two of them will actually collide and annihilate. It's the brightest spot on the dark matter map.
But it's also an incredibly messy and violent place, astronomically speaking.
Right.
You've got a supermassive black hole, exploding stars, pulsars, all sorts of things throwing out high-energy radiation.
And that's the monumental challenge. How do you listen for the faint, specific whisper of dark matter annihilation amidst the deafening roar of 1,000 other cosmic fireworks going off at the same time? That was the problem Professor Totani's team had to solve. And solving that problem required an instrument built for exactly this purpose. The data that Totani's team analyzed came from NASA's Fermi Gamma Ray Space Telescope. It's been orbiting Earth for years, mapping the sky in the highest energies of light.
So let's get right to it. The team sifts through all this data from the Galactic Center. What specific signal did they manage to pull out of all that noise?
After a very, very careful analysis, they isolated a gamma ray signal with a remarkably specific energy. The photons they found were clocked at 20 gigaelectron volts.
Okay, 20 GeV. Let's ground that number for a second. We hear these terms, but what does 20 billion electron volts actually mean? How energetic is that?
It's immense. For perspective, the light our eyes can see has an energy of maybe 2 or 3 electron volts. A medical X-ray might be a few thousand. We're talking about photons that are billions of times more energetic than visible light.
So it's an extremely high energy signature.
An incredibly high energy signature. And that's the first clue. An energy that high can really only come from a very energetic event, like the annihilation of a really massive particle. The more mass you start with, the more energy you get out.
So the energy level is the first perfect match. But the second clue, and maybe this is even more important, was the signal's shape and location.
Absolutely. If this was just, say, a pulsar, a spinning neutron star, you'd expect to see a single bright point of light. But that's not what they saw.
What did they see?
Totani described it as a distinct halo-like structure. It's not a point. It's a diffuse glow that's brightest toward the galactic center but extends outward, fading gradually.
That's the clincher, isn't it? That shape is a dead ringer for the theoretical models of the dark matter halo itself.
It's an almost perfect spatial match. You have a signal with the right energy showing up in the right place and distributed in the right shape. When you line all three of those up, the odds of it being some random astronomical object start to drop very, very quickly.
The observational data is lining up with the theoretical profile of a WIMPs. So let's talk about that profile. What does a 20 GeV gamma ray tell us about the WIMP that made it?
Well, this is where it gets really exciting for the particle physicists. You can work the math backwards. A gamma ray with 20 GeV of energy would be produced by the annihilation of WIMPs that each have a mass of roughly 500 times the mass of a proton.
500 proton masses. Now, is that significant? In the grand scheme of all the theories out there, where does a 500 proton mass particle fit?
It's extremely significant because it starts to narrow things down. For a long time, many of the most popular theories, especially those connected to supersymmetry, were predicting much heavier WIMPs, maybe thousands of times the mass of a proton.
So this is actually on the lighter side of what people were expecting.
It is. A WIMP with about 500 times a proton's mass is still very heavy, but it falls into a specific window that a lot of previous searches might have overlooked. It immediately forces theorists to look at a different set of models. Any new theory of dark matter now has to be able to produce a particle with this specific mass. It's a hard data point.
So you had the energy peak at 20 GeV. But not just a single spike, right? The annihilation should produce a whole spectrum of energies.
Yes, and that's another crucial piece of the puzzle. The overall shape of the energy signal they found, not just the peak, also aligns incredibly well with the spectrum you'd expect from WIMPs of this mass annihilating into other particles, like bottom quarks, for example.
It's the whole package.
Yeah.
The energy, the shape, the spectrum, it all fits.
It's a remarkably coherent picture.
But, as we said, the galactic center is chaos. How did they convince themselves, and how do they convince the rest of the world that this isn't just some other weird thing that also happens to produce 20 JV gamma rays?
That is the most difficult part of the analysis, and it's what makes this claim so credible. They had to systematically rule out everything else. Pulsars have the wrong energy spectrum. Cosmic rays hitting gas clouds produce gamma rays, but again, the shape and the spectrum don't match this halo.
And their main strategy was to look just outside the very center, right? To avoid the worst of the noise.
Exactly. They deliberately cut out the data from the central galactic plane itself because it's just saturated with radiation from known sources. They focused on the extended, diffuse glow around that noisy core.
So they looked at the subtle glow in the background, not the bright fireworks in the foreground.
Right. And by doing that, they isolated a signal that is, in their words, not easily explained by any of the usual suspects. When you've ruled out every known possibility, the one that remains, no matter how extraordinary, starts to look pretty compelling.
And the most compelling explanation left on the table is the annihilation of a 500-proton mass dark matter particle.
It all points in that direction. The energy, the distribution, the frequency, it all converges on that one WIMP model.
Okay, so this is the moment everything pivots.
Right.
If this signal holds up to scrutiny, if this really is WIMP annihilation, then we're not talking about a theory anymore.
We're talking about a real physical particle. As Professor Totani himself said, this would mark the first time humanity has seen dark matter.
And that leads directly to the massive consequences for physics, for the Standard Model.
The Standard Model of particle physics has been unbelievably successful. It describes all the known particles, all the forces, but it has these two huge glaring holes in it. It can't explain gravity, and it has absolutely nothing to say about dark matter.
So, if this WIMP is real, it is by definition a new particle. It's something that exists outside that beautiful, established framework.
It's the first definitive piece of evidence that the Standard Model is incomplete. This WIMP, it's massive, it interacts with the weak force, but it just doesn't fit anywhere on the current chart of quarks and leptons. It's like finding a new continent on a map you thought was finished.
It means you have to draw a new map.
You have to expand the theory. It means there's an entire dark sector of particles and forces that we've been totally oblivious to. It fundamentally changes our definition of what matter even is.
But a claim that big, one that rewrites the textbooks, requires an unbelievable amount of proof. This is where the scientific community goes from excitement to intense skepticism.
And rightly so. The burden of proof is enormous.
So what does that verification process actually look like? It can't just be one team's analysis.
No, absolutely not. There are two main lines of attack here. First is independent verification. Other teams of physicists around the world need to take the exact same public data from the Fermi telescope and run their own completely independent analysis.
Using their own methods, their own code, to see if they find the same thing.
Exactly. Can they filter out the background noise in their own way and still pull out that same 20 GeV halo? That's step one.
And what's step two?
Step two is finding the signal somewhere else. Finding it once in a very messy place is fantastic, but finding the exact same signal in a completely different, much cleaner environment, that would be undeniable.
This is the WIMP run you mentioned.
Yeah.
You need to find a cosmic clean room. A place that's packed with dark matter but doesn't have all the other astrophysical fireworks going off.
And we know exactly where to look for those. The perfect targets are the dwarf galaxies that orbit our own Milky Way.
Why are they so perfect for this?
Because they are completely dominated by dark matter. They have very few stars, so they're very dim, but they have a huge amount of mass for their size. Their mass-to-light ratio is off the charts.
And crucially, they're quiet.
They're very quiet. They don't have supermassive black holes at their centers. They're not forming lots of new stars. They don't have the chaos of the Milky Way's core. They are almost pure, clean laboratories for studying dark matter.
So if you point the Fermi telescope at one of these dwarf galaxies, and you see that same 20 GeV gamma ray signal.
Then you've got it. That's the nail in the coffin, because you've now seen the exact same fingerprint from the exact same particle in two radically different environments. The odds of that being a coincidence are practically zero.
That would be the moment you can confidently say you've discovered the dark matter particle.
That's what would provide the overwhelming evidence. And Professor Totani himself points this out. He says detecting this signal from dwarf galaxies would provide even stronger evidence that the gamma rays originate from dark matter. We're all basically waiting for that confirmation now.
It's just an incredible journey. You go from Fritz Wiki nearly a century ago, just looking at fuzzy smudges of light moving too fast, to today, where we're pinpointing the energy signature of their invisible components colliding.
It's a beautiful example of how theory and observation work together over decades. It shows that sometimes the biggest discoveries aren't about seeing something totally unexpected, but about finally building the tools to see something we knew deep down had to be there all along.
All right, so let's wrap up this deep dive and boil it down to the key takeaways, the things you should remember from this whole incredible story.
First, it all started with gravity. Zwicky in the 1930s saw that galaxies were moving too fast, which meant there had to be a huge amount of invisible or dark matter providing the extra gravitational glue.
Second, the main theory to explain this was the WIMP, the weakly interacting massive particle. And the key idea was that when two WIMPs collide, they annihilate and produce a detectable flash of high-energy gamma rays.
Third, that's the breakthrough. Professor Totani's team, using data from the Fermi telescope, found a signal that fits that description perfectly. A diffuse halo of gamma rays right at 20 GeV, near the galactic center.
And that signal is consistent with a WIMP that has a mass about 500 times that of a proton, a signal that can't be easily explained away by any other known astronomical source.
And if this gets confirmed, it's the first time we've ever seen dark matter, and it proves the existence of a new particle beyond the standard model. It literally changes physics.
And finally, the next crucial step is verification. Scientists are now looking for that exact same 20 GeV signature in the clean, quiet environments of dwarf galaxies. If they find it there, it's case closed.
So for you, the listener, you're now completely up to speed on what could be one of the biggest scientific revolutions of our lifetime. This isn't just an academic paper. It is fundamentally redrawing the map of our universe.
Which brings us to our final provocative thought. If we are just now, after 100 years, finally confirming the existence of the stuff that makes up 85% of all matter, it makes you wonder, doesn't it?
It really does.
If that much of the universe was completely invisible to us until now, what else is out there? What other particles, what other forces might be lurking just beyond the reach of our current technology, just waiting for the next Zwicky or the next Fermi telescope to bring them into the light?
The invisible universe might be far stranger and more complex than we can even begin to imagine.
A truly mind-bending thought. Thank you so much for joining us on this deep dive into one of the cosmos's greatest mysteries. Keep asking questions, and we'll see you next time.